Hello, my name is Mukh Patel. My ID is 24DCS079 and I am from Webster. And my topic is carbon nanotube field effect transistor, the future of post silicon computing in digital era. Carbon nanotube FETS, the future of computing. Explore carbon nanotube field effect transistor. They may overcome the limitation of the silicon. CNT FETS could power the next generation digital electronics. CNT FETS could power the next generation of the digital electronics by overcoming the limitation of the silicons. And this presentation includes the potential challenges and the future of this. So let's explore the topic carbon nanotube field effect transistor. Okay. So here's the introduction first. Introduction to digital electronics and post-silicon computing. Digital electronics overview and Moore's law and post-silicon computing. Digital electronics overview. Digital electronics rely on the binary signals. Binary signals means they talk in two digits only, 0 and 1, not in another language. Their language is run by 0 and 1 only. Processed by semiconductor devices such as transistor to perform logical operations, and this component forms the foundation of the modern electronics. These components form the foundation of the modern electronics, from processors to memory storage devices. It process from processor to memory storage devices, and these components are very useful. Secondly, we see Moore's law. Historically, Moore's law predicted that the number of transistors on the microchip would double approximately every 2 years. Microchip of the Moore's law, yeah, they have predicted that number of transistors on the microchip would double approximately every 2 years, which leads the increasing in the processing of the power and decreases the cost per transistor. And we know that how the cost is, that is very high, and it decreases the cost per transistor. So it is very useful to us. However, as we reach smaller and smaller nodes, that is below 5 nanometer, this exponential growth is no longer sustainable with current silicon technology. However, we reach to the smaller and smaller nodes such as 5 nanometer or etc. etc. This exponential growth is not so longer sustainable with silicon technologies as it goes smaller and smaller nodes and post silicon computing, with the limitation of the silicon based technology becoming increasingly evident. For example, heat dissipation, power consumption, quantum tunneling, post silicon materials such as carbon nanotubes, graphite, and gallium nitride are being researched for the potential to overcome this limitation. These are research for the potential to overcome this limitation. So here is the introduction to the digital electronics and post silicon computing. So we move to our next slide. Here's the impedance end of the Moore's law. Silicon limitation and scaling challenges. Silicon limitation. Moore's law faces physical limits such as quantum tunneling and heat dissipation becomes problematic. Moving beyond silicon is essential, and energy efficiency is major concern. Moving beyond silicon is very essential as there is a problem of energy and it is a major concern, and quantum tunneling and heat dissipation become the prominent ones while Moore's law faces physical limits. Here's the scaling challenges. Current silicon transistors are at 7 nanometer. Further shrinking to 2 nanometer, it is difficult. Moore's law may completely break down around 2025 because of the reason of the breaking of a nanometer breaking of transistor as it shrinks to the 2 nanometer, which is very difficult, and new material are also needed. So here we move to our next slide. Challenges of silicon-based electronics. Here's the challenges: miniaturization limits, power consumption, heat dissipation, and speed bottlenecks. Miniaturization limits, which contains short channel effects and quantum tunneling. As silicon transistors are miniaturized, several issues arising includes short channel effects. As transistors shrink, the gate's ability to control the current flow becomes less effective. leading to unwanted leakage. As the transistor shrinks, the gate's ability to control the current flows become less effective because they can't get enough space to move, and which leads to the unwanted leakage. Quantum tunneling, it is similar like to it, as at very small scale electron can tunnel through the gates by passing the channel and causing the significant leakage current. It is similar to the upper one short channel effect, as in upper one they would tell about the current, and here when electron passes to a small scale, the leakage current happens, which is the significant one cause of it. Power consumption. Power consumption increases significantly with scaling due to leakage current, sub-threshold swing, and parasitic capacitance to the interconnect of the interconnects, which is very important. Power consumption increases significantly with scaling with due to current leakage, and it's not the good sign. Heat dissipation. As transistor becomes the denser, they generate more heat. Silicon chips struggle to dissipate this heat efficiently, limiting their performance at smaller scale. Speed bottlenecks. The performance of silicon transistor faces a bottleneck due to increasing resistance in interconnects, which slows down the data transmission rate and limits overload processing speed. Sorry. Now we move to our next slide. Here's the understanding carbon nanotubes. First is cylindrical molecules, second is type of CNTs, and third is unique characteristic of it. Cylindrical molecules, as figure is shown here, CNTs are cylindrical molecules of carbon atoms. They possess exceptional properties. As you can see, the cylindrical shape of the carbon nanotubes. Types of CNTs, there are single walls and multi walls. And unique characteristics. CNTs exhibits high strength and excellent thermal conductivity. They also have exceptional electrical properties. Here's what is the field effect transistor. So here's the basic structure, working principle, and type of FETs. First of all, basic structure. A FET consists of three main terminals: source, drain, and gate. Here's the first one: source, the terminal where carriers enter the transistor, and drain, the terminal where carrier exits the transistor, and gate, the terminal that controls the flow of carriers by applying an electric field to modulate the channel conductivity. Here's the working principle. A voltage applied to the gate creates an electric field that modulates the conductivity of the challenge between the source and drain. Effects are crucial for controlling the flow of currents in digital circuits, enabling switching operations such as those used in logic gates. As the logic gates we know, and NOR, XOR, etc. etc. Types of FETs. MOSFETs, metal oxide semiconductor FETs, are the most common types used in modern digital circuits, which have a thin oxide layer acting as an insulator between the gate and the channel. Here's the end of it. The next slide. Advantage in digital electronics. Superior performance, lower power, and high density. CNT FETs have faster switching speed. Lower powers reduce the leakage current, improves energy efficiency. High density. Smaller devices size allow increased transistor density. Here's the end of this slide. Now the second slide. CNT FET structure and function. Basic structure, operating principle, key advantages. A CNT channels connect source and the drain electrons. A gate dielectric and gate electrodes are also present. An operating principle, gate voltage modulate CNT conductivity. Key advantages: higher carrier mobility and ballistics transport are present. Power consumption is lower than the silicon FETs. CNT FETs, concepts and working. What are the CNT FETs? CNT FETs are carbon nanotubes as the channel material in the transistor instead of traditional silicon. This device take advantage of superior electrical properties of CNTs, including their high electron mobility and low resistance. Working principle similar to the traditional MOSFETs. The gate of the CNT FET controls the flow of current between the source and drain by creating an electric field in the CNT channel. The gate voltage modulates the energy barrier for electron flow, switching the transistor on and off. CNT FETs exhibit an ultra-low sub-threshold swing, power consumption, and better performance. Here the challenges in fabrication, CNT purity, placement and alignment, contact resistance. CNT purity. Control is needed over metallic versus semiconducting CNTs. High purity is essential. Placement and alignment. Precise positioning is needed for optimal performance. Control resistance. Resistance between CNTs and electrodes must be minimized. Here's this three one. Let's move to the second one. Recent advances in overcoming challenges. CNT synthesis. Chemical vapor deposition is one approach. Arc discharge and laser ablation are also used. Alignment method. Self-assembly and dielectrophoresis are showing promises. Contact engineering. Metal CNT interference optimization is very crucial. Right? The recent advances of this. As a second, higher electron mobility. Carbon nanotube exhibit significantly higher electron mobility compared to the silicon. This allows CNT FETs to operate much faster, reducing the delay in switching times and enabling higher speed computation, lower power consumption. CNT FETs consume less power due to their lower leakage currents and sub-threshold swing. This is particularly beneficial for mobile devices and other battery powered applications. Miniaturization. CNTs can be scaled down to the atomic size, sub 1 nanometer, far surpassing silicon limitation. This enables the creation of this device smaller than the 5 nanotube nodes of the current silicon technology. And thermal management. CNTs have high thermal conductivity, which allows them to dissipate heat more efficiently. This reduces the risk of the thermal breakdown in the high performance devices, flexibility and durability, and the mechanical strength of the CNT, them suitable for the flexible electronics and variable devices that require the resilience and durability. Sorry for the interruption. Here the next, the high performance computing of the CAT. Supercomputing, high frequency application, and scalable architecture. CND FETs have the potential to be used in supercomputers for tasks requiring massive parallelism and high speed processing. High frequency applications have the fastest switching speeds of the CNTs, make them ideal for high frequency applications such as radio frequency circuit, analog signal processing, and wireless communication system. Scalable architecture has the ability of the scale CNT FETs to smaller size makes them ideal for the next generation processor, which demands higher transistor density and greater performance. Here's the variable and flexible electronics in the CNT FETs. Variables and stretchable electronics. Here's the first one. Variable CNT FETs can be used in the variable devices such as the smartwatch, fitness tracker, and health monitoring device. The flexibility, high strength, and the lower consumption makes them perfect for lightweight and flexible circuit. Here we're using the smartwatch as as in the nowadays. in today's generation, and the fitness tracker for the fitness things and all that, etc. And health monitoring devices, which give the flexibility, high strength, and lower power consumptions. Stretchable electronics. The CNT-based transistor can be integrated into stretchable circuits, allowing for the creation of the flexible and even comfortable electronics. These are the stretchable electronics. Manufacturing challenges for CNT FETs: synthesis, integration, and defects. Producing high quality CNT with consistent properties is still a challenge. Control over the charity of the CNT, whether they are metallic or semiconducting, so I don't doesn't matter, is is critical for the device performance. Integration. Integrating CNT into existing SOMOS fabrication processes poses significant challenges. Current processes are optimized for silicon and transistor to CNTs requires changes in fabrication and design. And there's the defects. CNT often contains structural defects that can be affect the device performance. These defects needed to be minimized for the real level operations. Real level. Here the performance matrices and benchmarking, speed, power efficiency, and scalability. It includes this in speed, faster switching speed; in power efficiency, lower power consumption, and scalability, some 1 nanometer nodes. Here's the future computing architecture. Sorry for this. Yes. Future computing architecture: microprocessor, memory, interconnects. High performance, low power processor are possible. Microprocessor, memory, high density, fast, non-volatile. Memory may be realized. Interconnect, high speed signal transmission can reduce signal delay. As we are facing the delays in signal when the network connectivity is problem, etc. Is such kind of that the high speed signal transmission. The road higher commercialization, 5 to 10 years, expert niche application, billions of funding, a significant investment in nanotechnology, collaboration, partnership between universities and research and companies, etc. etc. Yes, the conclusion is promising future. CNT offer advantages over silicon. Overcoming fabrication challenges is key. They may revolutionize digital electronics. Further research is crucial. The future of computing may depend on carbon nanotubes. So here's my topic of carbon nanotubes, which I am going to end. So thank you for it. Thank you for listening me. Thank you.